Nakikita na ba uli yung ating presentation? Okay.
Yes, sir.
Uh, okay, so going back here, no, dito sa with regards to positive and negative movement. So the analysis of T-beams actually occur when we have a positive movement, no? A positive yung movement natin because the flange and the web, no? Under compression yan kapag meron tayong positive movement, no? So usually yung positive movement sa mga continuous beam, okay, usually nag-occur yan at the midspan, no? Okay? So yung negative nasa support yan, okay? Nasa support. Okay, so going back here, no? Kapag yung isang case, no, sa T-beams ang kinonsider natin, okay, yung depth ng compression block nasa flange, okay, within the flange. So we will treat it as a rectangular beam. The way we treat a rectangular beam, no, in the compressive force will be computed only kung asan yung depth, no, wherein yung depth ng compression block. Ang pinagkaiba lang ngayon sa rectangular, yung pinaka-B natin dito, pinaka-width natin, we're going to use the width of the flange, no? Yung pinaka-width ng flange natin. Yun lang, no? But for the other case, itong letter D, no? Figure dito, the depth of the compression block is within the web. So there will be what? There will be a compressive force in the flange. So in solving for the compressive force, i-split natin, no, para madali yung computation. We will consider the compressive force in the flange and we'll consider the compressive force in the web. So yun lang ang pinagkaiba, no, nung dalawa. Okay? So then, no, we need to identify kung asan yung depth ng compression block for us to easily analyze, no, yung ating T-beams. Okay? So yun yung about this part, no. So usually yung positive moment ang kino-consider natin, no, in treating a T-beams, no. At tandaan natin, ang T-beams usually nag-occur yan if we have a what? A one-way slab, no? The distribution of the load in the slab is actually one half. No, one half of the slab will be distributed on the right side beam, while the other one half will be transferred to the left side beam. So creating now, or there's a possibility of behaving the beam as a T-beams, no? Usually sabi ko nga sa inyo, nag-occur to kapag malalapit yung ating mga beams, no, at one way yung ating transfer of load to sa ating slab. Okay, so sabi dito, if the neutral axis falls within the slab depth, meaning at the flange, no, analyze the beam as a rectangular beam, otherwise as a T-beam, no. Pag rectangular ka natin, yung ating area na i-consider dito will be the depth of for the compressive force, no, will be the depth of the compression block and also the width of the flange, no. Yun ang treatment natin. Whereas kapag T-beam yan, we're going to consider, we're going to split, no? We're going to split the compressive force in terms for the flange and in terms for the web. I think mamaya magkikita natin yan, no? Okay, so for the determination of the effective flange width, okay, this is how we have actually criteria, no, on how to determine the effective flange width. Okay, so mentioned here, portion near the web are more highly stressed than areas away from. Okay, so to visualize this, okay, we have now here, no, the stress distribution. Okay, ito yung ating stress distribution. It's actually parabolic in shape, no? Zero at the end, no? If we will have here a T-beam, okay, so it is zero here, then gradually increasing near the face of this beam. Okay, so dito maximum. So similarly on the other side, ganun din. Ngayon, to treat this or to simplify, no, the analysis, okay, we consider what we call a effective width, designated as BE. And this effective width, considering this effective width, we may able to assume that the distribution of the stress is uniform. Itong shaded part. Ito ngayon yung distribution ng stress. Okay? Near the face of this beam. Okay? So, yun yung ating assumption, no? By getting the effective width, we may able to convert this stress into uniform, no, distributed stress. Okay, so uniform siya, no, by considering the effective width. Now the effective width, okay, the determination of the effective width, so we have now this criteria. Okay, so the effective width can be equal or less than L over 4. L over 4 pertaining to the clear span. Ito yung clear span ng beam natin, no? So pag clear span ka natin, it is measured from face to face of the supporting column. So yun yung about this clear span, no? Yung L. So this L over 4. Then another criteria that we need to consider is equal or less than 16F. HF, what I mean. Yung HF dito, it is the thickness of the flange, no? Okay, thickness of the flange. Okay, so dito ang designation kasi natin T, no? But it's actually the thickness of the flange. Then plus BW. BW is the width of the web, no? Ito. Okay, itong web natin. So, yun yung another criteria, no? Then another criteria, it must be equal or less than B actual. So, B actual is actually the center to center spacing of beams, no? So, ano yung center to center? Ito, no? If we have here three succeeding beam, no? Okay, the center is actually measured from yung center to center, no? It is measured from the midspan, okay? Ditong onto the left, no? Onto the left, considering this middle beam, no? So we're going to consider the clear span dito sa ating slab. Ito yung pinaka-slab natin. Yung clear span niya, consider natin yung 1/2 of the clear span, no? Kaya ito kung S sub 1 nito, it will be S over 2. So we consider here S over 2. And then on this side, yung clear span dito ay S2. So we will consider 1/2 of S2. So S1 over 2 plus S2 over 2 plus BW. So that is about the center to center spacing, no? Between ano, no? In getting for the what do you call it? In getting for the okay, so or we can say it na para ma-simplify natin ito, no? So minsan kasi, no, medyo ano tayo, ito para mas madali, no? Ito. So if we will draw here a line representing the location of the center, no? Center of the beam, no? So this line representing the center, no? So it represents the center. Then another one here, center to center, okay? Ayan, no? So ang gagawin mo dyan, okay, you get the half of this distance, also the half of the distance here. Okay, you add those two half distances. Okay, that will be the center to center spacing between beams. Or we can say it na if we will get the span, the clear span of this slab, no? And get one half of this. Similarly, no? Ganun din dito sa kabila. We will get one half of the clear span and adding the width of the web, that will also represent the center to center spacing, no? That will also represent the center to center spacing between beams. Okay, so yun yung pangalawang criteria, no, na binabanggit. Okay, or pangatlong criteria na binabanggit, no? So center to center spacing of the beam. Now so these are now the three criteria that we're going to consider in determining the effective width of our T-beam. So we will select which of the three is the smallest. So yung pinakamaliit dito sa tatlo, siya yung mag-govern, no, to satisfy these three criteria, no? Okay? Now, what I've noticed, no, kasi ito kinuha ko doon sa bagong code, yung 2014 code, no, na ACI. So what I've noticed in the 2015 code, I think ito yung part na hindi, hindi kamukha, no, nung kamukha ng NSCP, okay? Nung NSCP. I think ang NSCP ang nakalagay ay BW plus ln over 4, no? Yung ln is the clear span. So ito rin yun, clear span. So yung bagong code, sinimplify na lang niya, no? That yung criteria is simply the clear span over 4. But in NSCP, kino-consider pa niya yung column width, no, yung BW na binabanggit, no? So if you have a column having a dimension of I think tama ba? Okay, I think the width of the beam, I'm sorry, no? Meron siyang BW. Okay, BW plus ln over 4, no? Yun yung NSCP. So BW pertains to the width, no? Width of the okay, width of the beam, no? Okay? So I will verify that, no? Ito na kasi yung na-cover kong criteria, no, do sa bagong code. Hindi ko na napansin yon doon sa NSCP, na yung NSCP hindi niya binago, no, yung criteria, okay, which is BW plus ln over 4, no. So yun yung about the NSCP, okay. But here yung L dito, it pertains to the clear span, no, clear span ito, which this criteria, no, I refer it from the new code from ACI, no. So do sa ACI. Kaso yung palang activity nyo, ang problema ng activity nyo, I put there specifically use NSCP 2015, no. Kaya medyo kung titignan nyo yung criteria, kulang, no, kulang yung data kasi what do you call it, anyway, we will check that, no. Ito ngayon yung ating ito yung ating another criteria for the L shape, no. But anyway, I think yung NSCP is BW plus ln over 4. That BW pertains to the width of the beam, no. Okay, so width of the beam, so ibig sabihin na makukuha pa rin, no. Kaya lang ang pinagkaiba nga lang ito, no. Dito kasi nakalagay ay L lang, walang N, no. Doon kasi sa NSCP LN, which is the clear span. So clear span din naman to, no. So this also clear span, okay. So anyway, yung binigay kong data, ang assumption natin doon clear span yon. Kasi wala akong binabanggit na column, no, o saan na measure yung L, no, na 4.5, no. So siguro ang maaari ninyong gawin doon, kung nag-compute man kayo, ang assumption natin doon will be the clear span, no. Clear span na yon, yung 4.5. So all you need is add yung BW ng beam natin, no, which is the width of the beam, okay. So I think the width of the beam is given in the problem, no, kung di ako nagkakamali, ha. Kaya makukuha pa rin nyo yung B effective using the NSCP. The only or ang hindi lang klaro kasi ngayon ito, no, kasi ang designation kasi dito nung iba, ito yung center to center spacing. Ito yung center to center measurement ng span ng beam, no. In other books, kapag letter L yan, capital letter L, it is measured from the center to center, okay. Center to center, which is measured from the center of the column, no. Okay, wherein in NSCP ang clear span sa kanya, ang designation ay LN, no, LN. Medyo yun ang problema ng NSCP kasi we are already using now yung mga karamihan yung mga books sa reinforced concrete kasi ano yan, puro American, no, puro American ng mga yan. Kaya makikita mo yung designation kapag gumamit ka ng bagong libro, no. Ang designation kasi dito, pag clear span ka natin, L na lang, no, L na lang, no. Kaya yun ang medyo conflict pagdating sa NSCP, okay. Yun yung version na code, but the problem, we do not have our own book, no, para NSCP lahat ang pinag-uusapan, no. We're just trying to make it compatible, no, doon sa mga bagong libro ngayon, no. Okay, so ginagawa na lang natin na compatible yan, okay. But the definition of this is actually clear span, okay. So doon sa activity nyo, I hope ginamit nyo na as a clear span yung given L, no. All you need is add BW for you to have the complete criteria for NSCP, no. Kasi merong nag-ano sa akin merong nag-message sa akin, hindi ko na nasagot dahil gabi na, no? So ngayon ko lang naalala, no? Okay. Okay, si Catherine, no? Nakalimutan niyang patayin yung kanyang microphone. Okay, klaro pa ba yung sounds ko sa inyo? Hello?
Yes, sir.
Sige, no? Kasing lumitaw dito sa screen ko, bad network at problema yung yung audio, no? So I don't know kung gaano ka yan, no? Okay, so yun yung about this, para hindi tayo mawala, no? So this criteria is based from the new code, ACI, no? And if you compare it to NSCP, no, itong part na to I think pagkakaiba, no? Meron ditong plus BW. Yung B actual dito is the center to center spacing of beams. So gaya ng nabanggit ko kanina sa inyo, it can be measured by taking 1/2 here, S1 over 2 plus S2 over 2 plus BW. So kagaya din yan ng center to center spacing, no? Okay, so for the inverted L shape, this is actually the criteria, no? So L over 12 plus BW, 6 HF plus BW, and BW plus 0.5 clear distance to the next web. So yung S, kung titignan natin dito sa drawing, okay, balik tayo dito, ito, no? Kung ano yung length mo dito, yung 1/2 dito, kaya 0.5 kanya, that is 1/2 of the clear span here, no? Tapos plus BW. Okay? So that will be the criteria, no? So yun yung ibig sabihin nito, no? Clear distance to the next web. Okay? So that is about the B actual. Kaya ginawa nilang general to, no? B actual. So that is between 1/2 of the clear span of the slab plus BW. Yun yung B actual na binabanggit. So sa mga middle beam, ito kasi corner or edge na beam ito, no? Yung nasa middle beam, yung B actual natin is measured center to center spacing of beam. Okay. Okay, for isolated beams, T-beams, this is how we check our HF and B effective. Okay, HF must be equal or greater than BW over 2, and then B effective must be equal or less than 4 multiplied by BW, no? So that is for isolated T-beams. Okay. Now, if we will in treating a twin T, no, just like what is shown here, you may convert it into a T-beam, just like this one. Then for box type beam, you may also convert them like this, no, for you to treat them as a T-beam. Okay, so ganun yung treatment natin, no? Okay, so let's move on now to the analysis of case 1. If we will consider case 1, wherein the depth of the compression block is equal or less than HF. HF, ito yung thickness ng slab, or the thickness of the flange. So if our A is within the flange, then the treatment is as a rectangular section. Okay, so in the analysis, the tensile reinforcement, we will assume the stress equal to Fy, or we will assume our tension still yields, and then we will check if really A is equal or less than HF. Okay, so ito yung binabanggit ko sa inyo kanina, na in treating it as a rectangular, the only difference is that B natin, okay, so yung B natin, ito pala, so I think our B now here will be the B effective. Okay, I hope tama. So magkikita rin natin mamaya, so B effective. Okay, because that is the what? That is the okay, so that is the area, area where our concrete is under compression. Okay, so that will be B here, so B E. Check natin mamaya, kung B nga to, so hindi kasi ayun, tama, we have here, so nandito pala, ayun, equal to 0.85 F prime C ABE, ayun, para hindi tayo mawala, so this is BE, hindi kasi nakalagay, but in this drawing, okay, the compressive force is 0.85 F prime C ABE, ayun, then you check now, you confirm it, if really A is less than or equal to HF using this formula. Now once it is equal or less than, so your computed A here will be verified on another assumption, ano yung assumption pa natin? Yung Fy, so we will check if really the steel yields, so ang gagawin mo ngayon, you check it, so you solve for the strain in the steel, if the strain in the steel is equal or less than the yield, so correct yung assumption mo. Now how about if the steel does not yield? Okay, kapag hindi nag-yield yung steel mo, okay, so ang gagawin mo ngayon, babalik ka dito, solve for Fs, so solve mo yung Fs. This time you're going to solve for C. Okay, solve mo yung C, tapos solve mo yung A, then you confirm again if A is equal or less than HF, so that's the way we analyze it, okay, for case 1. Okay, so once you have confirmed that your steel yield and A is equal or less than HF, you may use this formula. But then again, if your Fy does not yield, or if your steel does not yield, so you better solve Fs, so that's how you do it, Next, for case 2, for case 2, our A is greater than HF. Okay, meaning mag-yield yung steel mo, pagkatapos ang depth ng compression block mo is within the web, so magkakaroon ka ng dalawang compressive force. The compressive force in the flange will be solved using this formula. So ang ginawa lang dyan, kinat dito tsaka dito, tapos kinonsider yung flange, as a whole, so to get then the area of this, we simply multiply or we get the difference between BE and BW. So itong B dito, it pertains to the effective width, no? BE. Then multiply by HF o yung thickness nung flange natin, no? Or other, this is the thickness of the slab, no? Okay, now for the CW, ito naman, itong natitira dito, yun ang magiging BWA mo, no? Kasi yung A natin nandito, no? And then for your T, so your steel yield, no? Yan ang assumption natin. Then solve for A using equilibrium condition. So ito ngayon yung formula natin. If A is greater than HF, no? Ito yung pinaka-formula natin. And then once you solve for A, you check if your steel yields, no? Okay? Check muli yan. Pag nag-yield, actually ang the best equation para i-solve mo yung nominal strength, you make use of CW and CF. Okay? So yun ang pwede mong gamitin. Okay, so ito yung about the determination of CF and CW. Here, it is designated as C1 and C2. So for the flange, ito yon, no? So nakalagay dito BE minus BW, no? BE minus BW. Kaya ang equation natin ay 0.85 F prime C multiplied by the thickness of the flange or the thickness of the slab, BE minus BW. Now for the web, no? Sa web, yun, 0.85 F prime C A BW. Okay? Ito yung dalawang divided part na under compression. Okay? Okay, so ito yung ating mga formula. So naulit lang dito. Okay. For the 1999 code, okay, the determination of the ROMAX for T-beams, we have ROMAX equal to 0.75 raw balance. But the determination of raw balance, it is equal to AS balance over BWD. So the AS balance is equal to CC balance over FY. And CC balance is equal to CF balance plus CW balance. Yun ang pagkuha natin ng CC balance, no? Okay? So this for the 1999 code. Okay, for the new code, the ductility requirement, so same as for the singly reinforced beam, no? Kung paano natin kinukuha yung ductility requirements sa singly reinforced beam, so ganito rin, no? And then for the A minimum, so this is the formula. Ano rin ito rin yung raw min. Kaya lang nakalagay na yung BWD, no, para makuha mo area, no? Okay, so this is for flange in compression. Pero kapag yung flange mo in tension, ito naman yung AS minimum, no? So ang gagawin mo dito sa dalawa, pipiliin mo yung larger, i-compare mo dito, whichever is smaller naman. Yun naman ang mag-govern as AS minimum. This is for flange in tension. Ano ito, no? Kapag sa support, if you are treating a T-beam, no, do sa support kasi yung flange mo under tension. Okay? Okay, so lower limit, these are actually criteria from the code, no? AS provided must be equal or greater than 4/3 of the AS required based on analysis, no? Kapag yung AS provided mo, no, is equal or greater than the 4/3 AS required, AS minimum is not required. Okay. Also another another requirement from the ACI, our Vmn must be equal or greater than 4/3 mu. No? Okay, so that's another requirement. Okay, so let us solve this given problem. We're going to determine nominal design moment using the latest code, then AS max and AS minimum. So that is based from the AS max based from the 1999 code. Okay, so let us look at now itong given problem natin. No? So ito yon. Pag-analysis ka natin, the B effective is already given. No? It's already given in the problem. So what we're going to do is determine its adequacy or capacity. No? So kaya i-determine natin yung nominal at yung ating design moment strength. No? So these are now the given. The thickness of the flange is 75. The area of the tension reinforcement, AS. The effective depth is 412.5. Fy is 346 megapascal. Fc prime is 21 megapascal. Vw is 300 millimeters, and the clear span is 5.5 meters. So these are the required. No? So in the analysis, we will assume first that A is equal or less than HF. And our assumption is our steel will yield. No? So ito ngayon yung result, 76.28 millimeters. Then we will check, no? If okay, so our A is 76.28 millimeters. No? Our assumption is that A is equal or less than HF. No? Okay, so kung i-check natin ngayon, ano ba yung HF natin? Ang HF natin is 75. So meaning, the depth of the compression block is within the web. Kasi lumagpas na siya sa HF. Ang result ay 76.28. So A is greater than HF. So therefore, no, yung compression block natin lies on the web. Okay? So yun lang, no? Kagad makukuha natin kung A is equal or less than HF. So napakadali lang, no? Ngayon ang gawin mo ngayon, punta ka doon sa isang case, no? Your A is greater than HF. So itong A na nakuha mong to, hindi ito correct. Kasi ang assumption mo, A is equal or less than HF. And it shows here that A is greater than HF. So you did not satisfy the assumption here. Kaya itong A mo dito, incorrect. No? Incorrect ito. So you go now to the next case wherein your A is greater than HF. So ito ngayon yung ating pangalawang case. No? So wherein we need to solve for CF, CW, and T. No? So ito yung mga equation natin. And solving for A, okay, A now is 80.75. So tama ngayon yung assumption natin that A is greater than HF. So what we need now is to confirm if our tension reinforcement yields, no? Kung nag-yield nga yan. So ang gagawin natin ngayon, we will check the strain in the steel. And it shows here that the strain in the steel is greater than the yield strain. So therefore, the tension still yields. So our assumption is correct, no? That the tension still yield. Okay? So we may now proceed, no? Kasi tama ngayon yung ating A, itong 80.75, tsaka yung C natin. Tama na ngayon, no? Okay, because we satisfy all our assumption. So then, we may solve now for the nominal. Ito yung nominal strength natin, no? So this is your CW. Ito naman yung CF mo, no? So substitute the known values. Your MN is 688.05 kilonewton meter, no? So ito ngayon yung nominal strength ng ating beam, no? And then for the design strength, no? If we will make use of the NSCP 2015, okay, our net tensile strain, no, epsilon T is 0.010, and it is greater than 0.004. So therefore, our beam, no, is considered as a ductile section. Okay. Now, to determine the strength reduction factor, we will compare it, no, to the boundary, no, and it shows here that epsilon T is greater than 0.005. So therefore, we have a tension controlled section. So our phi is 0.90, and our phi MN now is 619 kilonewton meter. Okay. Now for the determination of the AS max using what? Yung old code, no? Ito yung computation natin, no? C balance, okay, greater than HF. Okay, ito yung formula. Now solving for A, we have beta 1C balance, no? Then yung CW balance natin, we have this formula, and CF balance, we have this, no? So adding these two will have your CC balance, and we may able to solve for AS balance. Then after solving AS balance, masosolve na natin yung AS max. So AS max is 0.75 AS balance, no? So that is how we solve AS max. Okay, so para at least may knowledge kayo on this part. Okay, then for the AS minimum, okay, so whichever is the larger of the two, yun ang mag-govern. So AS minimum is 500.72. Sa new code, ito pa rin, no? Yung pagkuha natin ng AS minimum, no? Ganito pa rin yung pagkuha natin sa bagong code. Okay? So I think yun yung solution ng problem natin. Kapag analysis yan, so we simply follow the procedure given dun sa ating call it, yung given sa ating lecture, no? Doon sa ating copy ng lecture natin, we just follow the procedure, no? Okay, so let's move on now to the design, no? Okay, design of T-beams, okay? Okay, so the case, no, wherein ito lang yung isa sa mga case na pwede nating i-consider, no, kapag nagdi-design tayo ng T-beams. If we have a known section dimension. Okay, meron pa kasi ibang case, no, wherein mas komplikado yung pagdi-design. Ito yung wala kang dimension, no? You do not have a known section dimension. Okay, you design a T-beam. Okay, but this is the common case when we design a T-beam, no? So having a known section dimension. So once we have this, we can determine actually yung tinatawag nating effective depth, no? But for the meantime, in the in the design, no? Okay. Kapag kasi wala kang known dimension, okay, wala kang known dimension, ito yung pwede mong gawin, no? Okay? Okay. So, ito yung pwede mong gawin pag wala kang dimension. Okay, so, ito yung rule of thumb na pwede natin gamitin. Yung depth ng section natin, pwede nating we can approximate it by taking 8 to 10% of the span. So, yung span ng beam mo, kunin mo yung 8 to 10% nun, no? That will be your H. And then, try to estimate B by taking 1/2 of H, no? So, 1/2 of your depth. So, pwede ito yung criteria mo, rule mo, no? Sa pagkuha ng dimension. Now, another one, we have this one, no? The weight of the rectangular beam will be about 15% of the superimposed load. You may assume that you may assume a B, and then B will be 1/2 of H, no? So yung B naman ang i-assume mo, then to get H, you simply multiply B by 2 to get H, no? Because your B is 1/2 of H, okay? So multiply mo lang ng 2 itong B natin, makukuha mo na yung H. So this is another way of having or approximating your dimension, okay? So yun, no? So pag nakakuha ka ng dimension, kunin mo yung self weight niya, i-check mo ngayon dito sa weight, no? Kailangan daw, no? Nasa 15% of the superimposed. Yung superimposed load, ito yung dead load mo tsaka live load mo, no? Aside from the self weight of the beam, which is considered as dead load. So kung ano yung superimposed mo, no? Yung dead load mo galing sa slab, galing sa wall, no? Those are your dead loads. So you check if your self weight based from your assumed dimension, if it is about 15% of the superimposed. So doon ka mag-a-adjust ngayon, no? Doon ka mag-a-adjust. Okay, so that is for the dimension, no? Okay? Kapag wala ka, pwede mong gamitin itong dalawang rule na to, no? Okay? Sa pag-approximate ng dimension ng section mo. Okay, next. Okay, so we have now here, no, for the design. Okay, so just like in double reinforced, no, kailangan meron kang MU. So this is the ultimate moment, no, the maximum moment from your load combination, and remember your load are factored, no. So yun yung MU na tinatawag, no. Then you may approximate now your effective depth, no? Pag single layer lang yung reinforcement mo, you may use this formula. Kapag double layer yung reinforcement mo, you may use this one. So remember, the reinforcement that we are talking about here is the tension reinforcement, tension, Then you determine now the nominal moment provided with compression in the flange alone. So yung flange lang, no? This is the compressive force given by the flange. Ayun, B effective multiplied by HF. Yung B effective natin, yun yung criteria, no? So kukunin mo yung criteria, gagamitin mo yung tatlong criteria, and then select the smallest. Yun ang magiging B effective mo. So once you have your compressive force, you may use this formula in determining the nominal moment capacity. And then you compare it to mu by applying strength reduction factor. Yung strength reduction factor natin, okay, we will assume it as equal to 0.90. No? No? Okay, so if mu is greater than PMF1, need to utilize Webb below flanges. No? So, ibig sabihin, hindi kakayanin ng flange na i-resist yung ultimate moment. Okay? If mu is equal or less than PMF1, so use design procedure for rectangular beam with your B equal to B effective. Okay? So, ibig sabihin, yung B effective nung ano mo, o yung B ng beam mo will be equal to B effective. Okay? So, yun. Then, D minus A over 2, no, approximated to 0.95D. Okay? So, yun yung ating criteria, no? Okay? So, you simply consider it as a rectangular beam procedure, no? Kung anong procedure sa rectangular beam, yun ang ipa-follow mo dito. Pero kapag mu is greater than, you proceed to step 4. Ito yung step 4, no? So, we will consider now our section as a T-beam, having now your CF, the compressive force in the flange, equal to this formula. And then MF, ito yung formula natin, no? So, tandaan natin, we only consider here yung flange, ha? Hindi kasali yung web. And then we will solve now for the moment, nominal moment capacity that must be provided by the web. Ito, no? MW. Kaya may W yan. This is the nominal moment capacity that must be provided by the web. Okay, so to get this, we will divide our mu by a reduction factor. So usually 0.90 ito minus mf, no? And then once you have your MW, you may solve for A. Okay, so solve mo ngayon yung A, no? Pag meron ka ng A, you check, no, all of your assumption, no? Okay, so eto ngayon yung pag-compute natin ng AS required, no? So by the way, once you have your A, ito pala yung gagawin mo, no? You're going to solve for the AS required, wherein A is used dito sa ASW, because CW is equal to 0.85 F prime CBWA, no? While ASF is CF over FY. Yung CF dito, ito rin yung formula mo. Ito. Kung ano yung formula mo dito, yun din yung gagamitin mo dito, no? Dito. Ha? And then you add this to, that will be the AS required. Ito yung ngayon yung reinforcement sa tension. No? This the AS required for our tension reinforcement. Okay, and then you may get now the number of bar by assuming a diameter, and then you get your AS provided. Okay, your AS provided must be equal or greater than the AS required. So to do this, kailangan mag-add ka ng 1 sa pagkuha ng AS provided, no? O pagkuha ng number of bars. Okay? Okay, so checking minimum reinforcement requirement. Okay, ito yung AS minimum, no? So this is your AS minimum. As mentioned in our presentation in the analysis, if AS provided is greater or equal to 4/3 AS required, you don't need AS minimum. Okay, but if AS provided is less than 4/3 AS required, so you need to consider AS minimum. Okay, so for the ductility requirement, no? So ito pa rin yung sa ating code, no? Okay, code requirement, and then you may compute your nominal. Okay, so nominal, and then also your your design moment strength. Okay, so we have now here yung problem natin. Okay, so let us look at yung solution ng problem natin. Okay, so we have here a floor system wherein the beams are spaced, measured from that is center to center spacing, no? Equal to 1.8 meters. So the width of the beam is 375 millimeters. The thickness of the slab is 75. The total depth of our beam is 650 millimeters. Given the strength, then given the length of our beam 5.4. So this is the clear span, no? Clear span of the beam. Then we have here moment dead load, moment live load, no? Okay, so estimate H equal to 650, B equal to 375. Okay, so that is about the problem. Okay, so it is not mentioned in the problem that our moment are already factored, no? Hindi binabanggit. Kaya ang gagawin natin, ipa-factor natin. So the dead load will be multiplied by 1.2. The moment in the live load will be multiplied by 1.6. And this is the load combination that will produce a maximum moment. So pag pinag-combine mo to, that will be the maximum moment. So 1,300 kilonewton meter. Now, the assumption is that we will have a 2-layer of bar. Kaya ito yung effective depth natin, no? Assumption. Okay, so we will select now what will be our effective width for our flange, no? So that is for our T-beam. So L over 4, 1,350, 16 HF plus B, 1,575, and center to center, it will be 1,800. Okay, so the smallest of the three is 1,350 millimeter. Okay, so ito yung mag-govern na B effective. Okay, so then now we will make use of B effective to solve for CF1, and then we will solve for MF1. Ito yung procedure na binigay kanina, no? We will solve first for CF1. Ito yung concrete or compressive force in the concrete that is considering only the flange, no? Yung flange lang. Okay, so your design moment strength for the flange is 1,260.6 kilonewton meter, and we will compare it to MU. So MU is 1,300 kilonewton meter, and MU is greater than VMF1. So therefore, we will consider this, no? We will design it as a TV. Okay. So next step will be, we will solve now CF1 or CF, what I mean, considering now as a T section, no? So T na to, no? Kasi dito, we only consider it as, this time, ito yung buong flange to no? Buong flange. Kasi B effective multiplied by HF. Ito naman, we already subtract the web, no? Yung web natin, ayan, B effective minus B, no? And then we will solve for MF. So that is 1011.59 kilonewton meter. And then we will subtract this to get the moment capacity for the web, no? For the web. Okay, so kita nyo, you just follow the procedure, no? And then, okay, we will solve for A, the depth of the compression block. So we will create here a quadratic equation. So dito nyo na makikita yung detailed part, no? Then we will solve for A, and A is 77.17. So it shows here that our A is on the web because HF is only 75, no? Ibig sabihin, yung ating depth of the compression block is within, is in the web, no? Is in the web. Okay? So yun yung ating A. Now, if we will solve for the AS required, so we will solve for ASF and ASWG. So ito ang inyong result, no? And this is now our AS provided. We will consider 36 millimeter diameter bar, so our number of bar is 7. Okay? Our arrangement, it will be in 2 layers. So ang arrangement natin 4 on the first layer and 3 on the second layer. So we will check if 4 bar is enough, is okay for 1 layer, no? So kailangan i-satisfy natin yung minimum clearance ng ating mga reinforcement. So it shows here that the clear spacing for 4 bars in 1 layer is 43.67. So this is greater than the minimum required. So it's okay that the first layer is in 4 and the second layer is in 3. If you try here 5, it will be less than 25. Kaya hindi pwede yung 5. 4 lang ang pwede, no? Okay, so then, no, if we will check now our AS provided, it will be equal to 7,125.13. So this is the provided, while the required is only 6,496, no? So it is greater than. Kaya na satisfy natin yung isang requirement do sa procedure, no? And then we will also check if AS provided is less than 4/3. If it is less than 4/3 AS required, okay, we need to check AS minimum, no? So yung AS minimum natin, ang gagawin natin ganito, no? Kukunin natin yung centroid ng group of bar dahil magkakaroon tayo ng gagamitin natin yung effective cover para makuha natin yung effective depth. And remember, the effective cover here is measured from the center of the group of bar up to the bottom side of the beam, no? So that's why here, no, itong part na to, kinuha natin yung Y bar. No? So I will not go on the detail here. It is purely what, using Varignon's theorem, ha? Varignon's theorem lang to, no? So Y bar is 26.14, and this is now our effective cover, and our effective depth is 555. 0.86 millimeter. So then we may solve now AS minimum and AS minimum, no? So AS minimum will be 704.895. So whichever is the larger of the two, yun ang mag-govern. And we will compare it to AS provided, no? So AS provided is greater than AS minimum. So ibig sabihin, yung criteria natin na AS provided is what? Is less than, no? So yung ating AS provided is within the limit, no? It is greater than AS minimum, no? So it is we satisfy AS minimum, okay? Now for the ductility requirement, we will check first, no? Okay. So ito, no? Ito ngayon yung design natin, no? Wherein our tension reinforcement will be 7. Our arrangement will be 4 on the first layer and 3 on the second layer. So in accepting this design, we check the AS provided and also we check the AS minimum. So we satisfy this requirement, no? Now, the next part is to analyze, no? Analyze naman natin. We will check the adequacy, no? We will check the adequacy. Okay, so we will determine now the nominal moment capacity, assuming that A is greater than HF. So diretso na tayo, ano? Hindi na tayo pupunta pa doon sa A is less than. So punta na tayo doon sa A greater than, ha? Okay, so our BW will be B. Okay, so we will have CF plus CW equal to T if A is greater than HF. Solving for A is 103.52 and it is greater than HF. So we satisfy our assumption. Okay, so our compression block lies on the web. Then we will check if our tension reinforcement yield. Okay, so epsilon S is greater than the yield. So therefore, tension still yield. Our assumption again is correct, no? So once correct na lahat ng mga to, ibig sabihin your A here is correct, your C is also correct, no? Your computed A and C. We may now solve for the nominal. Ito ngayon yung nominal natin, no? Okay, and then we will check ductility. Okay, it shows here that our section is ductile, no? And for the strength reduction factor, it is 0.9. And this is now our moment capacity. Our moment capacity, our design moment strength now is greater than MU. No? Yung MU natin is only what? Ano yung MU natin? Okay. Our MU is 1,300. Our moment capacity, so konti lang yung tinaas, no? Ha? It is equal to 1,363, no? Okay, so therefore we may say now, you may conclude now, no, adopt the design. Okay, so yun yung about the design of T-beams. Okay, so once you have your reinforcement, the next step is you analyze. You get your nominal strength, okay, then also your design moment, okay, by taking the ductility requirement and the strength reduction factor. Okay, so I think you already have an idea on how to analyze, no? How to analyze analyze T-beams, no, by following this lecture, no. Okay, yung activity nyo, yung laboratory activity nyo is actually what? A combination of what we have done in analysis and design, no? Kasi yung binigay kong activity sa inyo, wala kayong effective width. Pero do sa example kasi natin, di tayo kumuha nun. It's already given. No? But in your laboratory, hahanapin nyo. No? Hahanapin nyo wherein nakita natin yan dun sa design, no? Kung paano kumuha ng effective width, no? But you're going to follow NSCP, no? Okay? So I think ito yung ano nyo, no? So you're going to follow NSCP. Yung 4.5 dito, this is already the clear span, no? Clear span na to, no? 4.5 meters. So all you need is add BW for you to get or for you to satisfy or for you to compute the one of the criteria in the selection of BW, B effective, no? Okay? So ito yung laboratory exercise nyo, ha? So I think I'm done with T-beams, no? Design and analysis. Okay, so tandaan natin, no? Look at your activity here. Okay? Kagaya nung binabanggit ko sa inyo kanina, T-beams occur kapag malalapit yung mga beams mo. Just like this one, no? Look at here, 1.8 meters. Okay? So, ito ginagawa to sa mga building na yun, iniiwasan nila yung mahabang beam, no? Iniiwasan nila yung magkaroon ng mahabang beam, or they want yung slab nila na one way, no? Okay, one way. Okay, ayaw nila yung two-way slab, no? Okay, so ganon, no? So yan, so dito tayo nagkakaroon ng mga T-beams, okay? Kapag malalapit yung spacing ng ating mga beams, okay? Okay, questions? Okay, about T-beams. So do you have questions? Okay, I'm going to check now the attendance. Okay. So since